Swayam Prabha. Digital India. Educated India.
Hello and welcome back everyone. We are learning the basics of building construction. Today we are going to start a new module on concrete. First we are going to talk about plain cement concrete today, and in the next lecture we are going to deal with RCC. So let's get started. What do we mean by cement concrete? Cement concrete is actually a building material which is obtained by mixing cement, sand, aggregate and water. This is done in a suitable proportion, and ultimately this plastic mixture is cured to ensure that it forms a hard mass. Now hardened cement resembles stone in its weight, hardness and strength, and the properties of concrete will ultimately depend upon factors like the quantity and proportion of the ingredients in the mixture, the placement of the concrete mix in the formwork, and the duration of the curing which is provided for the hardening of concrete. Let's learn a little bit about the first material which is mixed, that is cement. Now cement in its broad meaning refers to any substance which can act as a binding agent of materials. The cement used for construction process is produced by calcining a mixture of calcareous, silicous and aluminous substances at high temperature and then crushing the resulting clinkers to a fine powder. Now it is the most costly component of the concrete mix, and it may be available in different forms. We will learn about the different forms today. Now depending on the chemical properties, cement can be classified broadly into two categories. The first is called Portland cement and the other special cement. We can classify cement into various types. The first is Portland cement. So let's see what are the subtypes of Portland cement available. We can have ordinary Portland cement, rapid hardening Portland cement, extra rapid hardening cement, low heat Portland cement, Portland blast furnace slag cement, followed by Portland pozzolana cement, sulfate resisting cement and white and colored Portland cement. Cement can also be special cement, which can be divided into masonry cement, triumph cement, expansive cement, oil well cements. There are other types of cements available as well, which includes high alumina cement, super sulfated cement and natural cements. So this in totality are the broad types of cements which are available. We are going to learn in detail about each of them. First, let's get started with Portland cement and its subtypes. Now Portland cement is the most widely used variety of cement, and it is named Portland because of its resemblance to a well-known natural stone which is quarried in Portland. It is composed of some argillaceous or silicates of alumina in the form of clays and shales, or calcareous or calcium carbonate in the form of limestone, chalk and marl, which is a mixture of clay and calcium carbonate. Now if we see what are the chief chemical components of Portland cement, we will see that it has lime, silica, alumina, iron oxide, magnesia, sulfur trioxide and soda or potash. So we can see that lime and silica forms the major part of the composition, followed by the rest of the materials. Even alumina is proportionately higher than the rest of the types. During the process of setting, Portland cement undergoes certain phases of transformation. In the beginning it is tricalcium silicate. This remains active for from the early setting to about 7 days time. Then we see dicalcium silicate, which is active after 7 days to about 1 year. Then comes tricalcium aluminate, which is active after 1 year, and then tetracalcium aluminoferrite, which is comparatively inactive and responsible for undesirable properties of concrete. So this will actually lead to deterioration in the concrete that we have produced. In the process of hardening from paste to a hard mass, cement undergoes two types of settings. The first is called initial set. This is the phase where the cement paste gradually loses its plasticity and it becomes sufficiently coherent to withstand a certain arbitrary pressure. Now, the initial setting is completed within the 24 hours of laying of the concrete. Now, the second part of setting is known as the final set. In this phase, where the cement hardens further and it becomes rigid with time, it becomes strong enough to withstand higher intensity pressures. Now, the final set phase can take over at least a period of 28 days, where the concrete is cured every day by adding or sprinkling water on top of it. Now, let's learn a little bit about the types of Portland cement that we had listed in the beginning. Portland cement, just to quickly remind you, could be of these following types. We are going to take a look at each of them now. First is called ordinary Portland cement. Now, this is the most basic type of cement and it is commonly used for general constructions where there is no exposure to sulfates in the soil or the groundwater. Now, this follows specifications which are listed in IS 269. The next type is called rapid hardening Portland cement. Now, this cement is also known as high early strength cement. Now, why it is so is because it attains greater strength at an early stage. This gives us lots of advantages. For example, the formwork can be removed easily. We can do it earlier than we could do in the other types of cement. As a result, the cost of renting the formwork is reduced in the project. This also allows us to complete our project faster. This type of cement also follows specifications which are listed in IS 269. The third type is the extra rapid hardening cement. This is obtained by intergrinding calcium chloride with rapid hardening Portland cement, which imparts it quick setting properties. Due to this, the concrete should be placed and fully compacted within the first 20 minutes of mixing. The next type is called low heat Portland cement. This gains strength a little slower than other cement types, but the final strength is the same. This is used in massive constructions like abutments, retaining walls, dams, etc., where the rate at which heat can be lost at the surface is lower than at the rate at which the heat is generated. Now, it has a lower percentage of tricalcium aluminate and tricalcium silicate and a higher percentage of dicalcium silicate in comparison to ordinary Portland cement. Portland blast furnace cement, as the name suggests, is actually made by intergrinding Portland cement clinker with blast furnace slag, where the slag is not less than 25% or more than 65% by weight of cement. This is used in all buildings and structural construction types. It takes more time to gain strength in comparison to ordinary Portland cement. Sulfate resisting cement, which is the next type, the quantity of tricalcium aluminate is strictly limited. This needs to allow to harden in the air for a longer duration to form a resistant skin through carbonation by atmospheric carbon dioxide. Portland pozzolana cement is manufactured by intergrinding Portland cement clinker and pozzolana or by uniformly blending Portland cement and fine pozzolana. Now, as per IS 1489, the proportion of pozzolana may vary from 10 to 25% by weight of cement. If we compare the strength of Portland pozzolana cement with ordinary cement at the different ages, we will see that in the early time, that is say about 3 days, the compressive strength in Newton per millimeter square of Portland pozzolana cement is about 20 to 22, whereas ordinary cement ranges between 19 to 23. Similarly, at 7 days, the compressive strength of Portland pozzolana cement is 26 to 33, whereas that in ordinary cement is 27 to 32. At 28 days, this ranges from 37 to 48 in the first case, whereas in ordinary cement it is 36 to 52. So, the range of values of compressive strength are different in the two types. White and colored Portland cements are manufactured with the help of say 1% of iron oxide. So, you are basically adding a coloring agent to it to generate some color. So, 10% to the ordinary or white cement during grinder or clinker of colored pigments is added to give the colored look to the Portland cement. Special types of cement include masonry cement, trife cement, expansive cement and oil well cements. Other types include high alumina cement, super sulfated cement and natural cements. The first type of special cement, that is masonry cement. In this case, the Portland cement with lime has been used as a mortar for laying brickwork to achieve rapid strength. Usual proportions of the cement is to lime is to sand may vary from 1:1:6 or 1:3:12 for lighter loads. Now, they have water retentive properties helping to increase adhesion to the bricks or other building units, therefore making them preferable. Trife cement is similar to blast furnace cement, except that the blast furnace slag is ground wet and separated from the cement. It gains higher strength early on in the setting process, and this results in lesser shrinkage and small heat of evolution in comparison to ordinary Portland cement. Expansive cements expands during the hardening process. It is useful in repair works where open joints are to be filled with cement to obtain a tight joint. It is commonly used for underpinning processes and for repair of bomb damaged arch bridges in France. Oil well cements, in this case a cement used for filling the space between steel lining tubes and walls of wells when we are drilling oil wells, etc. This type of cement finds usefulness there. It is used as a grout up porous strata to prevent water or gas from gaining access to the oil bearing strata, and it is required to harden very quickly after setting. The properties are achieved by adjusting the composition of cement or by addition of retarders to the ordinary Portland cement. So, this allows us to quickly harden it. High alumina cement is also known as aluminous cement containing chalk and bauxite as the main chemical components. It is more expensive to produce in comparison to Portland cement, but it produces greater strength in concrete. This also requires higher maintenance and care. The super sulfate cement is made from well granulated blast furnace slag. About 80 to 85% of the composition is granulated blast furnace slag, and 10 to 15% of it is made with calcium sulfate, and 1 to 2% is Portland cement. Now, the concrete can expand or shrink when subjected to water and air respectively, and it offers higher resistance to chemical attacks. Natural cements are manufactured from naturally occurring cement rocks having a composition which is similar to the artificial mix of Portland cement. Now, that was all about the different compositions and types of cement. Let's learn now how we can store cement, because that's a bit tricky. Now, this requires extra care to preserve the quality and fitness for use, and the major requirement is to store the cement away from moisture. Now, in monsoons or in situations when necessary to store the cement for a longer period of time, the cement bags should be covered and enclosed in either polythene sheet or with a waterproof membrane material. Now, how do we store cements? What's the process? First of all, we have to get a room with minimum number of windows and close fitted doors. This is to ensure that not a lot of moisture enters into the space. The wooden planks are then laid down on the ground, ensuring that there is at least 150 mm gap to the floor and the place or the platform on which the cement bags are being kept. We also have to ensure that there is a 450 to 600 mm gap from the exterior walls or from the other stacks of cement. Cement bags are then stacked on these wooden planks such that we do not exceed more than 15 bags in a stack. The stacks are also arranged in such a way that the older cement bags can be taken out first to be used in construction, so that the ones which are newer we'll use later. So, this is what it would look like. As you can see, it is placed on a platform, a raised platform, so that it is not in direct contact with the ground. Even the ground is actually covered with a polythene sheet to ensure that less amount of moisture rises up. Overall, this space doesn't have much windows and it has very closely fitted doors. not more than 15 bags will be stacked vertically, and we will stack it in such a way that the newer bags are taken out later. Now let's learn about the specifications for Portland cement. To understand that we are using the right kind of cement and that it is of proper quality, we can perform several tests to check the quality of our cement. Now the properties of concrete or mortar largely depend upon the quality of the cement that we are using in the mix. So in India, the quality of the cement is tested as per the specifications which are provided in IS 269 by the Bureau of Indian Standards. And to maintain the quality of cement, there are 7 types of tests we perform to ensure that it is the right kind. First of all, we check for the chemical composition of the cement. Then we check for fineness and soundness of the cement. The setting time is also important, followed by the tensile strength and the compressive strength of the cement, and finally the heat of hydration. Based on these types, we can check the quality of the cement, and we can also determine what is the right place and right purpose for which this type of cement can be used. So first, when we are testing for the chemical composition of cement, this test is done in accordance to the methods which are given in IS 4032-1985, both for the ordinary as well as the rapid hardening Portland cement. They need to comply with the following conditions. First of all, the ratio of percentage of lime to the percentage of silica, alumina and iron oxide, this is calculated using this particular formula. This should not be greater than 1.02 and not less than 0.66. Next, the ratio of percentage of alumina to that of iron oxide should not be less than 0.66. Third, the weight of insoluble residue should not be more than 2%. The weight of magnesia should not be more than 6%, and the total sulfur content should not be more than 2.75%. Total loss in ignition should not be more than 4%. So with this, we can ensure that the chemical composition of cement is within the permissible limits. When tested in accordance to the methods as listed in 4032-1968, the low heat Portland cement should comply with the following chemical composition. Here, the percentage of lime necessary to combine with sulfuric anhydride should not be more than this particular equation. Here, it should be ranging between 2.4 silicon dioxide plus 1.2 aluminium oxide plus 0.65 ferric oxide, and it should not be less than 1.9 silicon dioxide plus 1.2 aluminium oxide plus 0.65 ferric oxide. So the second two components, that is aluminium oxide and ferric oxide, range is the same, but we are changing the silicon dioxide. It should not be more than 2.4, it should not be less than 1.9. So that was testing for the chemical composition of cement. Now the next item that we are going to check for is the fineness. Now fineness refers to the size of the particle of cement, and this is tested with the help of Blair's air permeability method. The description of this test can be found in IS 4031-1968. Now in this method, the cement is measured as a specific surface by observing the time that a constant amount of air passes through a compacted cement bed, and that gives us the definition of the fineness and porosity. In case of different types of cement, we can see that the ordinary cement, the fineness of the cement should not be less than 2250. For rapid hardening type of cement, it should not be less than 3250, and for low heat, it should not be less than 3200. This will give us an idea about the fineness of cement. The next thing that we measure is the soundness of cement. Now this is the ability of the cement to resist volume expansion and retain its original volume while it is setting and hardening. This is tested with the help of the Le Chatelier's method, which is described in the same IS code. Here, unaerated ordinary rapid hardening and low heat Portland cement shall not have expansion more than 10 mm. The next thing that we look at is the setting time. Now, setting time of cements when tested by the Vicat apparatus method, it should conform to the requirements as listed below. The initial setting time in minutes should not be less than 30 for ordinary, 30 for rapid hardening and 60 for low heat type of cement. The final setting time in minutes should not be more than 600 for each of these types. The heat of hydration is the next item that we look at. This requirement should apply only to low heat cement. When tested as per the method which is described in the mentioned IS code, the heat of hydration of low heat Portland cement shall be as follows. In 7 days, it should not be more than 65 calories per gram, and in 28 days, it should not be more than 75 calories per gram. The next thing we test for is the compressive strength of cement. To do that, the average compressive strength of at least 3 mortar cubes is taken. These mortar cubes are composed of 1 part of cement, 3 parts of standard sand by weight and P by 4 plus 3% water, which is prepared and stored as per the IS code as mentioned. Now let's learn a little bit about aggregates. The word aggregate actually refers to any inert or chemically inactive material which when bonded together with cement forms concrete. Mostly these are naturally occurring and it may include crushed rocks, gravel and sand, whereas artificially processed aggregates may include broken bricks or crushed air-cooled blast furnace slag. We can classify this into 2 broad categories. Aggregates can be coarse aggregate or fine aggregate. Coarse aggregates are bigger in size, they are more than 4.75 mm in size, and fine aggregates are less than 4.75 mm in size. Coarse aggregates, in this case, the size of coarse aggregate usually depends on the nature of the work. Natural gravel which are quarried from pits can be used. Coarse aggregates can also be obtained by crushing various types of granites, schist, gneiss, crystalline hard limestone and good quality sandstones. For high strength concrete, fine grained granite is preferable. Coarse grained rocks make harsh concrete, increase the need to add high proportion of sand and higher water cement ratio. As you can see here that we can have rounded, irregular or angular shapes for our coarse aggregate. Depending upon the context in which we are using it, what is the application we are putting it to, we can select the type of coarse aggregate and the shape of coarse aggregate that is applicable to us. Fine aggregates are smaller in size. Natural sands are generally used as fine aggregates and these are obtained from pits, rivers or seashores. They should be thoroughly washed before using it to remove any form of clay, silt or other impurities which may be present in the fine aggregates. Angular grained sand produces good quality strong concrete due to better interlocking properties. We can have, as you can see, angular coarse sand. This is an example of coarse sand. We can have medium or even fine sand. So as you can see, the size of the particles is different. The quality of aggregates are defined by 11 important characteristics. This include strength, size, particle shape, impermeability, chemical inertness, surface texture, grading, cleanliness, of course the cost, physical and chemical stability and the coefficient of thermal expansion. We also need to grade our aggregates. Now gradation of aggregates has a marked effect on the workability, uniformity and finishing qualities of concrete. So for gradation we are actually trying to see what are the various sizes of aggregates that we are having in a particular mixture. They can be single size mixture, we can have poorly graded where we have a mixture of many sizes together, and it can also be well graded where we have a proper flow or proper size put together in a particular mixture. The finest modulus of an aggregate is an index number which is roughly proportional to the average size of the particle in the aggregate. The coarser the aggregate, the higher is the fineness modulus. The fineness modulus is obtained by adding the percentage of weight of materials retained on the following IS sieves, and we are dividing that number by 100. So we can have these sizes. We can have 80 mm, 40 mm, 20 mm, 10 mm, 4.75 mm sizes. We can also go smaller. We can have 2.36, 1.18, and then in 600, 300 or 150 micron sizes. So as we can see here, there can be different sieves which are available to allow us to segregate particles of different sizes. So as you can see, if the gaps in these sieves are more, the larger size of aggregates will get caught in it, and as we go towards the smaller sizes, very tiny particles will also get caught in this sieve. So this allows us to segregate a big mixture of aggregates into its constituent sizes composition. So we can segregate them based on size, and then we can of course mix them together as already mentioned when we were grading of the aggregates. So we can actually take the sizes which are suitable in the mixture that we are going for based on the walkability, the uniformity that we are looking for in our mixture. We can then mix them according to the proportion that we require. Next, the very important component which will ensure very much how well this concrete mixture will perform is water. Now, water acts as a lubricant for the fine and coarse aggregates and acts chemically with the cement to form the binding paste. It is also used for curing of the concrete after it has been cast into the forms. So, from the initial part of setting to 28 days when we are curing the concrete, we definitely have to sprinkle it with water throughout that entire period. Now, potable water is generally considered satisfactory for cement concrete works. We do not want to use water which has a lot of impurities in it, because it is going to negatively impact the performance of this concrete. Now, if the water contains any sugar or has an excess of any acid, alkali or salt, that water should not be used. The following checks should be made before using of water for cement concrete works. First is that carbonates and bicarbonates of sodium and potassium, this reduces the strength of concrete. So we want to avoid that in our water. Chlorides and sulfates should be within the range of 3000 to 10,000 parts per million. Calcium chloride accelerates the setting and hardening process. It is tolerable at about 2% by weight of cement. Other inorganic salts like salts of manganese, tin, zinc, copper and lead reduce the strength of concrete. Hence, the water that we are using, it should be tested to ensure that these are either within a proportion permissible or avoided altogether. Turbidity is due to the presence of silt in the water, and it should be limited to 200 parts per million. Seawater containing up to 3.5% salts may be used for unreinforced concrete. However, it is undesirable when we are using this for reinforced concrete due to the high risk of corrosion from seawater. Acidic and alkaline waters are tolerable limit of hydrochloric, sulfuric and other common inorganic acids is about 10,000 parts per million. The presence of algae in the water can also reduce the strength of concrete that we finally produce. So we should check that algae is also not present in the water. Coming to the measurement of materials for the cement concrete mix, here the cement, it is measured in terms of weight instead of volume. In India, the cement is supplied in bags. Each bag is about 50 kgs. The coarse aggregate, it should be such that no bulking is noted, and it may be measured by either volume or by weight. And IS standard specifies that while we are measuring this, some amount of testing of the volume can be done with the help of containers. Maximum size of the aggregates, say 5 mm to 40 mm, 15 litre capacity cylinder is taken of 20 centimeter dia, and the maximum size of aggregates, if it is more than 40 mm, 40 litre capacity cylinder of 35 centimeter dia is used, and these are used to actually control the quantity of volume or weight that of coarse aggregates that we are adding to our mixture. Now, in case of fine aggregates, sand may be measured in weight for accurate works and by volume for ordinary works. Now, bulking of sand, that is the increase in volume of sand due to absorption of water, should be considered when we are measuring it by volume, because if we do not take that into consideration, the volume might be higher than what we were hoping to have in our mixture. Now, the bulking depends on the gradation and the fineness of sand as well. So, that means we are going to have to be very careful in the previous stage where we were talking about the testing of the gradation and the fineness. We have to ensure that it is just right, so that later on when we are mixing it, bulking is avoided. Now, water which is added to this mixture is measured by volume. So, it is basically measured as these many liters per bag of cement. For given quantity of concrete, adjustments in water also depends on the aggregates due to bulking action, of course. Therefore, making addition or subtraction based on the water requirements. So, that is, if we are having more bulking, that the volume is increasing, we will have to accordingly restrict the amount of water we are adding to the mixture. The next thing we need to look at is the water cement ratio, and this is of utmost importance. Now, the ratio of the volume of water mixed in concrete to the volume of cement used is known as the water cement ratio. The strength and workability of concrete depends to a great extent on the amount of water that is used. Use of less water produces brittle cement concrete, whereas use of excessive water produces low strength, increasing shrinking and decreasing the density and durability of the concrete. Now, according to Abram's water cement ratio law, for any given condition of test, the strength of a workable concrete mix is dependent only on the water cement ratio. So, lesser the water cement ratio, greater is the strength. So, according to Power, cement does not combine chemically with more than half the quantity of water in the mix. Cement required about 1/5 to 1/4 of the weight of water to produce and become completely hydrated. So, this also suggests that if in a water cement ratio we are having less than 0.4 to 0.5, then complete hydration will not be secured. So, a minimum quantity of water is required for the cement to be completely hydrated. All the water we are giving above that is in excess. And we should also note that the compressive strength will keep on reducing as we keep increasing the amount of water in the water cement ratio, as evident from this curve. So, let us take a quick recap before ending today's lecture. First, let us take a quick look again at the composition of Portland cement. Portland cement's chief components include lime, which is about 60 to 67%, followed by silica, which is about 17 to 25%, and this forms in totality the major bulk of Portland cement. Alumina is 3 to 8%, followed by iron oxide, which is 0.5 to 6%. Magnesia is 0.1 to 4%. Sulfur trioxide is 1 to 3%. Soda or potash is 0.5 to 1.3%. So, basically Portland cement is composed of argillaceous or silicates of alumina in the form of clays and shales, calcareous or calcium carbonate in the form of limestone, chalk and marl is also a part of it. Marl here is a mixture of clay and calcium carbonate. We can categorize cement into various subtypes. Predominantly cement can be either Portland cement, we can have special cements and other types of cements. Portland cement can be ordinary Portland cement, rapid hardening Portland cement, extra rapid hardening cement, low heat Portland cement, Portland blast furnace slag cement, Portland pozzolana cement, sulfate resisting cement, and white and colored Portland cement, where a certain percentage of pigment is added to give this cement a certain color. So, based on the purpose for which we want to use, the location at which it's going to be coming up, what is the environmental or weather elements that it will be exposed to, we can choose the type of cement that is applicable to us. Special cements can be further subcategorized as masonry cement, trife cement, expansive cement and oil well cements. Other types of cements are high alumina cement, super sulfated cement and natural cements. Natural cements are made from natural occurring substances and they have a composition similar to what we are doing in artificially manufactured cements. To check that the type of cement that we are using is of the right quality and has the right consistency and composition, we are going to have to do certain tests. Now these tests include, first of all, the chemical composition test. We want to ensure that the chemical composition is in the right range. We also check for the fineness and the soundness of cement, followed by the setting time. Now based on our application, it is important for us to know what is the setting time of cement. In certain locations or certain purposes, we need the cement to set faster as opposed to others. So depending on this result, we should know that what type of cement is applicable to us. We also have to check for the tensile strength and the compressive strength, and finally the heat of hydration of the cement. Similarly, we also have aggregates. Now aggregates are going to be mixed to our cement. Now these aggregates can either be coarse aggregate or they can be fine aggregate. Coarse aggregate are the ones which are more than 4.75 mm in size, and fine aggregates are smaller than 4.75 mm. With respect to aggregates also, we have a lot of characteristics that we have to look at before we use it. So the tests include for strength, size, particle shape, impermeability, chemical inertness, the surface texture, their grading, their cleanliness, and of course cost, physical and chemical stability, and the coefficient of thermal expansion. So with respect to aggregates also, we have to check whether these criteria are within the specified ranges. These are some of the references that you can take a look at for further study. With that, we end the first part of our module on PCC and RCC. Today we studied PCC. In the next lecture, we are going to continue this discussion and take it further, understanding how reinforced cement concrete is made. Thank you for tuning in today.